In the past two lectures, we talked about a number of problems that could be modeled as integer programs. So we talked about covering problems. We talked about problems with fixed costs, fixed charges. We talked about problems with either-or constraints, and we talked about problems with piecewise linear objective functions. And we saw how we could model all these problems by using integer programs. And that work was on modeling. We saw all kinds of interesting situations that could be modeled as integer programs. But so far, we do not have an algorithm for solving an integer program. And in this lecture, we're going to develop an algorithm that is going to allow us to solve an integer program. Okay. So our job today is to design an algorithm that is going to allow us to solve an integer program. And at the end of today's lecture, we're going to see that we can solve an integer program by solving a whole bunch of linear programs. So as a result of that, it'll be the case that solving an integer program is much more computationally intensive than solving a linear program, because just to solve one integer program, we need to solve a whole bunch of linear programs. But on the flip side of the coin, we can solve an integer program by solving a whole bunch of linear programs, and we have our simplex method for solving a linear program. As a result, we'll be able to solve an integer program by using our simplex method for solving many linear programs. Okay, good. So let's go ahead and design our algorithm for solving an integer program. And we're going to use an example to design our algorithm for solving an integer program. Here's what our example is going to look like. So let's say we want to solve an integer program that looks like this. We have 4 decision variables, x1, x2, x3, x4. We're maximizing the objective function 5x1 plus 4x2 plus 4x3 plus 3x4. Subject to these 4 constraints, our decision variables are non-negative, and the decision variables x1, x2, and x3 are restricted to the integer. Decision variable x4 can take fractional values. Okay, so this is the integer program. This is the integer program that we would like to solve. Here's our objective function, 4 constraints, non-negative the constraints in our decision variables, and the decision variables x1, x2, x3 are restricted to be integers. x4 can take fractional values. Okay, so how do I solve this integer program? So the first thing we're going to do is we're going to solve this integer program by ignoring the integrality requirements. We're going to solve this integer program by ignoring the integrality requirements. So we're going to solve this problem without the integrality requirements. So let me write my integer program without the integrality requirements. Let's just write that problem down. Maximize the same objective function, 5x1 plus 4x2 plus 4x3 plus 3x4, subject to the same 4 constraints, 2x1, 4x2, 3x3, 2x4 less than or equal to 20, 6x1, 5x2, 4x3 plus 5x4 is less than or equal to 25. Sum of the x's is greater or equal to 5. x2 plus 2x3 less than or equal to 7. And then non-negative the constraints. Same problem without the integrality requirements. Okay. This is a linear program. We know how to solve this linear program. Simplex method solves this problem for us. Okay. Let's go ahead and solve this linear program by using the simplex method. Let's say that by some pure luck, let's say that the optimal solution to this linear program satisfies all the integrality requirements. Let's say that by some pure luck, the optimal solution to this linear program on the right satisfies all the integrality requirements. That means that even without imposing the integrality requirements, I get an integer solution for free. So then the optimal solution to this linear program is also an optimal solution to the integer program. Then I'm done. Okay. Once again, let's say that we solve our integer program by ignoring the integrality requirements. Here's that problem. Here's my integer program without the integrality requirements. Let's say that by some pure luck, the optimal solution to this linear program satisfies all the integrality requirements. That means that without imposing any of the integrality requirements, I obtain an integral solution for free. That means that the optimal solution to this linear program is also an optimal solution to the integer program that I would like to solve. Then I'm done. But what is more likely to happen is that we solve this linear program, and the optimal solution to this linear program does not satisfy the integrality requirements. Then we need to do more thinking. Okay, so now let's go ahead and solve this linear program. Let's see what the optimal solution to this linear program is. And I'm going to use Groby to solve the linear programs that we solve along the road. We know how to solve a linear program already, but I'm just going to use Groby to solve the linear programs that we faced along the way. Okay, let's go to our desktop. In the desktop, I created a text file that includes the linear program that we would like to solve in the LP format. So here is the objective function that we want to maximize, subject to the four constraints, and we do not need to write down the non-negative constraints explicitly. Groby already interprets the decision variables as non-negative unless otherwise noted. So let's solve this linear program. Let's solve this linear program. Let's solve this linear program by using just Groby. My file is on the desktop. Okay. Good. So let's read that file. Let's solve that file. Let's solve that linear program. So the optimal objective value of that linear program comes out to be 23.1666. And let's look at the optimal solution. The optimal solution is x1 is equal to 1.83, x3 is equal to 3.85, x2 and x4 are equal to 0. So this is the optimal solution. Good. So let's record that solution. We solved this linear program, and the optimal objective value was the optimal objective value to this linear program was 23.167. And the optimal solution is x1 is equal to 1.83, x2 is equal to 0, x3 is equal to 3.5, x4 is equal to 0. Good. So we solved this linear program. This is the optimal objective value of this linear program, and this is the optimal solution. Does the optimal solution to this linear program satisfy the integrality requirements? No. I wanted x1 to be integer, but in the optimal solution to this linear program, x1 is equal to 1.83. I wanted x3 to be integer. In the optimal solution to this linear program, x3 took value 3.5. It also violates the integrality constraint. So then here's what we're going to do. We're going to pick one of the decision variables that violates the integrality constraints in the optimal solution to the linear program. Okay. So in the optimal solution to this linear program, we're going to pick one of the decision variables, x1 or x3, that violates the integrality requirements. Let's pick x1 arbitrarily. So x1 took the value 1.83. x1 took the value 1.83. There is the value 1.83. And the closest integers to 1.83 are 1 and 2. Okay. I wanted x1 to take an integer value in my original integer program, but in the optimal solution to this linear program, x1 took the value 1.83. Okay. I'm not happy with this solution. I'm not happy with this value for x1 in the optimal solution. I'm not happy with this value 1.83 in the optimal solution, because in the optimal solution, I want x1 to be integer. In other words, I want x1 to be either less than or equal to 1 or greater than or equal to 2, but nothing in between, strictly 1 and 2. Okay. So then based on the optimal solution to this linear program that we solved on the right, we're going to branch into two cases. We're going to branch into two cases. The first branch is going to branch into x1 is less than or equal to 1. The second branch is going to branch into the case x1 is greater than or equal to 2. So here's our first branch. That is going to branch into x1 is less than or equal to 1 case. And here's our second branch. And the second branch is going to branch into x1 is greater than or equal to 2 case. And in each one of these two branches, we're going to solve a linear program. On the left branch, we're going to solve a linear program that includes all the constraints at the top, plus the constraint that x1 is less than or equal to 1. And on the right branch, we're going to solve a linear program that includes all the constraints at the top, plus the constraint that x1 is greater than or equal to 2. Let's write the linear programs that we're going to solve in each of the left and the right branches. In the left branch, we're going to solve a linear program that includes all the constraints at the top, plus the constraint that x1 is less than or equal to 1. So on the left branch, I'm going to solve a linear program that maximizes the same objective function. All of the constraints at the top plus the constraint that x1 is less than or equal to 1. All of the constraints at the top plus the constraint that x1 is less than or equal to 1, and also the non-negativity on my decision variables. So this is the linear program that I solve at the left branch, and the linear program that I solve at the right branch is the same linear program at the top plus the constraint that x1 is greater than or equal to 2. Same constraints at the top plus the constraint that x1 is greater or equal to 2, and the non-negativity on our decision variables. Okay. So then in the left branch, we're going to look for the best integer solution that satisfies the constraint that x1 is less than or equal to 1. On the right branch, we're going to look for the best integer solution that satisfies the constraint that x1 is greater than or equal to 2. Okay. So let's solve the linear program that corresponds to the left branch, which is the linear program that we had before, plus the constraint that x1 is less than or equal to 1. Let's solve the linear program on the left branch. Here is the linear program that we solve on the left branch. Whatever linear program that we had before, plus the constraint that x1 is less than or equal to 1. Let's save this file. Let's read that file. Let's optimize, and let's look at the solution. So for the linear program that we solve on the left branch, the optimal objective value is 22.33. The optimal solution is x1 is equal to 1, x2 is equal to 1.67, x3 is equal to 2.67, x4 is equal to 0. Let's record that solution and the optimal objective value. So for the linear program that we solve at the left branch, the optimal objective is 22.3. And the optimal solution is x1 is equal to 1, x2 is equal to 1.67, x3 is equal to 2.67, and x4 is equal to 0. Good. So now let's make a few observations. Observation number 1. In the linear program that we solve at the top, the value of the decision variable, in the linear program that we solve at the top, the optimal value of the decision variable x1 was 1.83. In the linear program that we solve at the top, the optimal value of the decision variable x1 was 1.83. And we branch into the cases x1 is less than or equal to 1, x1 is greater or equal to 2. So that means that the optimal solution to the linear program that we solve at the top can never be an optimal solution to the linear program that we solve at the bottom. And why is that? In this optimal solution, we have x1 is equal to 1.83. In the linear program that we solve in the branch on the left-hand side, we impose the constraint that x1 is less than or equal to 1. So the optimal solution linear program at the top can never be a feasible solution to the linear program at the bottom on the left, because we're imposing the constraint that x1 is less than or equal to 1. So then the optimal solution linear program that we solve at the top can never be an optimal solution linear program that we solve at the bottom on the right-hand side. The same logic happens over here as well. Here we have x1 taking value 1.83 at the optimal solution linear program at the top. For the linear program that we solve at the bottom, we impose the constraint that x1 is greater or equal to 2. So the optimal solution for a linear program that we solve at the top can never be an optimal solution linear program that we solve at the bottom on the right-hand side either. Okay. And the linear program that we solve at the top, we call this as the linear program at the parent node. And we call these linear programs at the child nodes. So our first observation is that the optimal solution to linear program at the parent node can never be an optimal solution to linear program at a child node. Okay, so let's write that observation. So our first observation is that 1, the optimal solution to the linear program at the parent node, the optimal solution to the linear program at the parent node can never be the optimal solution to the linear program at the child node. Good. So that's one observation. Our second observation is that the linear program that we solve at the child node includes more constraints than the linear program that we solve at the parent node. Let's say it again. The linear program that we solve at the child node includes more constraints than the linear program at the child node, which means that the optimal objective value to linear program that we solve at the child node is always worse than the optimal objective value to linear program that we solve at the parent node. Okay. Let's see it again. The linear program that we solve at the child node includes more constraints than the linear program that we solve at the parent node. That means that the optimal objective value of the linear program that we solve at the child node is always worse than the optimal objective value of the linear program that we solve at the parent node. Let's write observation down as well. Observation 2, the optimal objective value of the linear program at the child node, the optimal objective value of the linear program at the child node is always worse than the optimal objective value of the linear program at the parent node. And interpret worse here as a soft sense, meaning that the optimal objective value of the linear program at the child node is always less than or equal to the optimal objective value of the linear program at the parent node. So as we go down, the optimal objective values of these linear programs are going to get worse because the linear programs at the child nodes are including more constraints than linear programs at the parent node. Okay, good. So far, we did all these linear programs, 1 at the parent node and 2 at the children node. Let's put all of these linear programs in an object that looks like a tree. Let's put all of these linear programs in an object that looks like a tree. Here we go. At the beginning of our tree, we saw this linear program at the top. So let's call this linear program as the linear program at node 0. This is the linear program that's at the top. The optimal objective value of this linear program came out to be 23.167. And the optimal solution to this linear program came out to be 1.83, 0, 3.5, and 0. So that is what happened at the very beginning. Great. So then we said, well, x1 doesn't satisfy the integrality requirement that I want. x3 doesn't satisfy the integrality requirement that I want. Arbitrarily, we picked x1. Based on the value of x1, let's branch into 2 cases. And the 2 cases that we branch into were x1 is less than or equal to 1, and x1 is greater or equal to 2. And that gave us linear programs at the 2 nodes. Let's call those 2 nodes as node 2, node 1, and node 2. Good. The linear program in node 1 includes all of the constraints in node 0 plus the constraint that x1 is less than or equal to 1. And the linear program in node 2 includes all of the constraints in node 0 plus the constraint that x1 is greater than or equal to 2. Okay. The linear program in node 1 includes all of the constraints in node 0 plus the constraint that x1 is less than or equal to 1. And linear program in node 2 includes all of the constraints in node 0 plus the constraint that x1 is greater than or equal to 2. And we saw the problem in node 1. We saw the linear program in node 1. When we saw the linear program in node 1, the optimal objective value came out to be 22.3, and the optimal solution came out to be 1, 1.67, 2.67, and 0. Let's write down the results for node 1. In node 1, the optimal objective value in node 1 came out to be 22.333, 22.3, and the optimal solution came out to be 1, 1.67, 2.67, and 0. So this is how far we went. This is how far we went. Okay. So now we look at the solution in node 1. Does the solution in node 1 satisfy the integrality requirements? I want x1, x2, and x3 to be integers. x1 is integer, but x2 and x3 are not integers. So the solution in node 1 does not satisfy the integrality requirements either. I take one of the decision variables in node 1 that doesn't satisfy the integrality requirements. Let's take x2, 1.67, that doesn't satisfy the integrality requirements. Based on the value of x2, which takes value 1.67, we're going to branch into two cases in node 1. And the two cases that we branch into in node 1 is going to be x2 is less than or equal to 1, and x2 is greater than or equal to 2. In the optimal solution to node 1, again, x2 takes value 1.67, and we want x2 to take an integer value. So then based on the value of x2 in node 1, we're going to branch to two cases, which are x1 is less than or equal to 1, and x1 is greater than or equal to 2. Here are those two cases that we branch into from node 1. Okay. So this is the first branch. x2 is less than or equal to 1. This is the second branch. x2 is greater than or equal to 2. So let's call this node 3. Let's call this node 4. Good. So now, how many nodes do we have unsolved? We have node 2 unsolved. We have node 3 unsolved. We have node 4 unsolved. We got to figure out the next node to solve. And there are different rules that we can follow to figure out the next node to solve. In our exercise, in our example that we're doing over here, we're going to use a depth first kind of a strategy. So we're going to solve the deepest node first, which means that we're going to solve node 3 or 4 first. Let's go ahead and solve node 3 first. Another strategy could be breadth first. So we could solve the node that is at the top next. So we could be going for node 2 first. And there is no well-known rule. There is no well-known reason as to which node we should be selecting next. Should we go depth first? Should we go breadth first? And there is no, again, well-established rule that's going to get to the optimal solution fastest. Going depth first ensures that we impose more constraints on our decision variables early on, which means that we're going to get to an integer solution as fast as possible. That's why we're going to follow the depth first strategy. But the nice thing about following a breadth first strategy could be that you could be exploring nodes that are more likely to give you larger objective values. That's a reason why you could be going for the breadth first type of a strategy. But again, there is no well-established reason as to which rule is going to give us a optimal solution faster. For our exercise, we're going to go for the depth first rule. We're going to go for the deepest node that hasn't been solved yet. So we could gonna solve node 3 or node 4. Let's go for node 3. So the linear program that we solve in node 3, includes all the constraints that we solve in node 0, plus the constraint that x1 is less than or equal to 1, plus the constraint that x2 is less than or equal to 1. Okay, so the linear program that we solve in node 3 includes all of the constraints in node 0, plus the constraint that x1 is less than or equal to 1, plus the constraint at x2 is less than 1. So let's solve the linear program in node 3. So linear program that we solve in node 3 constraint includes all of the constraints in node 0, plus the constraint that x1 is less than 1, plus the constraint that x2 is less than or equal to 1. Save. Let's solve this linear program by using Groby. Save. Read the linear program, optimize the linear program. The optimal objective value in this node is 22.2. Look at the optimal solution, 1, 1, 3, and 0.4. Good. So then we solve the problem at node 3. The optimal objective value is 22.2. And the optimal solution is 1, 1, 3, 0.4. Good. Right. So now we look at the solution. Does this solution, so this is the solution that we obtain in node 3, the optimal objective value in node 3 is 22.2, and the optimal solution that we obtain in node 3 is 1, 1, 3, and 0.4. Does this solution satisfy the integrality requirements? Does it? I wanted x1, x2, and x3 to take integer values. In this solution, x1 and x2 and x3 take integer values. So here I obtain a feasible solution to our integer program that gives us an objective value of 22.2. So now let's record that. Let's record that. Let's record that. And let's say that best objective value that we obtained so far, best integer objective value that we obtained so far is 22.2. And the best solution that we obtained so far, best integer solution that we obtained so far is 1, 1, 3, and 0.4. Good. So now, should we dig deeper into node 3? As we dig deeper and deeper into node 3, we know that the optimal objective values of the linear programs that we get as we dig deeper and deeper into node 3 are going to worse than 22.2. We already have an integer solution that gives us an objective value of 22.2. There is no reason that to dig deeper and deeper into node 3. We don't dig deeper and deeper into node 3. We stop the search at node 3. We don't dig deeper and deeper into node 3. So then that observation gives us one reason to stop the search at a particular node. If the optimal objective value of the linear program at the current node gives us a feasible solution to the integer program that satisfies all the integrality requirements, then there is no reason to dig deeper and deeper into that node because we already have an integer solution at this node. If I dig deeper and deeper and deeper this node, I'm going to get other solutions that give us worse and worse objective values, but I already have a solution that gives me an objective value of 22.2. If I dig deeper and deeper and deeper into this node, I'm not going to get anything better than 22.2. Why bother digging into this node? So now we have our first reason to stop the search at a particular node. And let's write that reason. And that reason is, if the linear program at the current, if the optimal solution to the linear program at the current node gives us a feasible solution to the integer program satisfying all integrality requirements, then we can stop the search at that node. So now let's say reasons stop the search at a node. So the first reason we figured out was if the optimal solution to the linear program at the current node is feasible to the integer program satisfying all integrality constraints, then stop the search at the current node. Good. So the optimal solution linear program that we solve in node 3 satisfies all integrality requirements. So then I have an integer solution that gives me an objective value of 22.2. If I dig deeper and deeper and deeper into node 3, the objective values I'm going to get are going to get worse and worse and worse. So I already have an integer solution that gives me an objective value of 22.2. There is no reason to dig deeper into node 3. So then I look at my tree now, Are there any nodes that have been left unexplored yet? Yes, node 4 and node 2. By our depth first strategy, we're going to solve node 4 next. The linear program that we solve in node 4 includes the linear program that we solve in node 4, includes all of the constraints in node 0, plus the constraint x1 is less than or equal to 1, plus the constraint that x2 is greater than or equal to 2. So then the linear program that we solve in node 4 includes all the constraints in node 0, plus the constraint that x1 is less than or equal to 1, plus the constraint that x2 is greater than or equal to 2. Right? So let's save this linear program. Let's read that linear program, solve that linear program. We get an objective value of 22.16. Now let's look at the optimal solution to this linear program. Good. This is the optimal solution. X1 is equal to 0.83, x2 is equal to 2, x3 is equal to 2.5. Let's record that optimal solution. We solved node 4, we solved node 4, we solved node 4. Great. So the optimal objective value in node 4, what is it? 22.167. And the optimal solution we get in node 4 is x1 is equal to 0.83, x3 is equal to 2, x3 is equal to 2.5, x4 is equal to 0. Right. Good. So now, let's look at what's happening in node 4. We solved the linear program in node 4. The optimal objective of the linear program came out to be 2.167 in node 4, and this is the optimal solution linear program. The optimal objective value of the linear program in node 4 is 22.167. The optimal objective value of the linear program in node 4 is 22.167. I already have an integer solution that gives me an objective value of 22.2, which is better than 22.167. If I dig deeper and deeper and deeper into node 4, I'm going to find worse and worse and worse objective values. But we already have an integer solution that gives us an objective value of 22.2. Then there is no reason to dig deeper and deeper into node 4. So there is another reason to stop the search at a particular node. Why is that? If the optimal objective value of the linear program at the current node is worse than the objective value of the best integer solution that we found so far, then we can stop the search at that node. Because if I dig deeper and deeper and deeper into this node, I'm going to only find worse and worse and worse objective values, but I already have an integer objective value of 22.2. I don't need to dig deeper into node 4. Let's say it again. Let's say it again. We solved a linear program corresponding to node 4. The optimal objective value of the linear program corresponding to node 4 is 22.16, but I already have an integer solution that gives me an objective value of 22.2. The objective value of the linear program that I solved for node 4 is worse than the objective value of the best integer solution that we found so far. If I dig deeper and deeper and deeper into node 4, I'm only going to get objective values worse than 22.16, but I already have an integer solution that gives me an objective value of 22.2, so there is no reason to dig deeper into node 4. So then here's another reason to stop the search at a particular node. So our second reason for stopping the search at a particular node is that if the optimal objective value of the linear program at the current node is worse than the objective value of the best integer solution that we found so far, then we stop the search at the current node. If the optimal objective value of the linear program at the current node is worse than the objective value of the best integer solution that we found so far, then we can stop the search at the current node. If the optimal objective value of the LP at the current node is worse than the objective value of the best integer solution we found so far, then stop the search at the current node. Good. We solve the linear program in node 4. The optimal objective value of linear program in node 4 is 22.16. I already have an integer solution that gives me an objective value of 22.2. If I dig deeper and deeper and deeper into node 4, I'm only going to get objective values worse than 22.16. So I already have a solution that gives me an objective value of 22.2. There is no reason to dig deeper into node 4. I'm not going to find anything better than the best integer solution that I found so far under node 4. So then we look at our tree. What is the node that has been unexplored yet? Node 2 is unexplored. Node 2, the linear program in node 2 includes all constraints in node 0 plus the constraint that x1 is greater or equal to 2. Good. So then linear program that we solve in node 2, the linear program that we solve in node 2, the linear program that we solve in node 2 includes all the constraints in node 0 plus the constraint that x1 is greater or equal to 2. Good. So let's solve this linear program. Read, optimize. The optimal objective value of linear program in node 2 is 23. And look at the solution. x1 is equal to, x3 is equal to 3.25. The others are 0. Okay. So then the optimal objective value of the linear program that we solve in node 2 is 23. And the optimal solution is x1 is equal to 2, x2 is equal to 0, x3 is equal to 3.5, x4 is equal to 0. Great. Here's the optimal objective value of the LP that we're solving node 2, and here's the optimal solution. Okay. Is the optimal solution in node 2? Does the optimal solution in node 2 satisfy all integrality requirements? No. x3 is non-integer. Is the optimal objective value of the LP in node 2 worse than the objective value of the best integer solution that we found so far? No. So there may be a better integer solutions hidden under node 2. So we're going to keep on exploring underneath node 2. Based on the solution that we obtain in node 2, how am I going to branch? x1 and x2 satisfies the integrality requirements, but x3 doesn't. So x3 takes value 3.5. So in node 2, we're going to branch into two cases. x3 is less than or equal to 3, and x3 is greater than or equal to 4. Those are our branches. So that is going to take us to, let's label these nodes as node 5 and node 6. Good. So now going by our first rule, we can either go for node 5, we can either go for node 6. Let's go for node 5. The linear program that we solve in node 5 includes all the constraints for a linear program in node 0, plus the constraint x1 is greater than or equal to 2, plus the constraint x3 is less than or equal to 3. So the linear program that we solve in node 5 includes everything in node 0, plus the constraint x1 is greater than or equal to 2, and plus the constraint x3 is less than or equal to 3. Good. Save this linear program. Read it, solve it. The optimal objective value in node 5 is 22.83. And let's also look at the optimal solution. x1 is equal to 2.16, x3 is equal to 3. So then, here's what's happening in node 5. The optimal objective value in node 5 is what? 22.83. And the optimal solution is x1 is 2.167, x2 is 0, x3 is 3, x4 is 0. So that's what we got in node 5. Good. That is the situation in node 5. So then we ask ourselves, are we going to stop in node 5? Question number 1. In node 5, did we get a solution that satisfies all the integrality requirements? No. X1 here violates the integrality requirements. We'll ask ourselves, is the optimal objective value for the linear program in node 5 worse than the objective value of best integer solution that we found so far? No. The optimal objective value of linear program in node 5 is 22.83. The objective value of the best integer solution that we found so far is 22.2. So this objective value is not worse than the objective value of the best integer solution that we found so far. So that maybe digging under node 5, we can reach better integer solutions. So we're going to keep on digging under node 5. So based on the solution that we obtain in node 5, we're going to branch. X1 is a decision variable that violates the integrality requirements. So let's branch into two cases based on the value of X1. X1 takes value 2.167, so we're going to branch into the cases X1 is less than or equal to 2, and X1 is greater than or equal to 3. Let's dig deeper. Let's make it like this. So here's our first branch. X1 is less than or equal to 2. And that takes us to a new node. Let's call that node 7. And we're going to branch into another case. We're going to branch into another case, and that is X1 is greater than or equal to 3. That also takes us a new node. And let's call that node 8. Good. So that's the current status of our tree. What nodes are unexplored? 7, 8, and 6. Going by the first, we're going to explore 7 or 8. Let's go for node 7. The node that we saw, the linear program that we saw in node 7, includes all the constraints in node 0, plus the constraint x1 is greater than or equal to 2, x3 is less than or equal to 3, and x1 is less than or equal to 2. So let's put those constraints. So linear program that we saw in node 7 includes everything that we have at the beginning, plus x1 is greater than or equal to 2, x3 is less than or equal to 3, and x1 is less than or equal to 2. X1 is greater than or equal to 2, x3 is less than or equal to 3, and also x1 is less than or equal to 2. There we go. There we go. Let's save this. Let's save this. Save. Read the linear program, optimize the linear program, look at the solution. The optimal objective of linear program that we solve in node 7 is 22.8, and the optimal solution is x1 is 2, x3 is equal to 0.2, and x3 is equal to 3, and x4 is equal to 0. Great. So then let's write what's happening in node 7. The optimal objective value is 22.8. And the optimal solution is x1 is equal to 2, x2 is equal to 0.2, x3 is equal to 3, x4 is equal to 0. That is situation in node 7. Good. So now we again ask ourselves, is the solution that we obtain in node 7 satisfying the integrality requirements? No, x2 takes fractional values here, so we cannot stop for that reason. Question number 2 is the optimal objective value of the linear program, in node 7 worse than the objective value of the best integer solution that we found so far? No. The optimal objective value of the linear program in this node is 22.8. The best integer solution that we found so far gives us an objective value of 22.2. So by digging deeper into node 7, we might be able to find another solution, another integer solution that gives us an objective value better than 22.2. So we're going to dig deeper into node 7. So based on the decision variable that violates the integrality constraint, we're going to branch into two nodes in node 7. So that is decision variable x2. X2 is taking the value 0.2. So we're going to branch into two cases. X2 is less than or equal to 0, and x2 is greater than or equal to 1. Good. And that gives us the nodes, node 9, and node 10. Okay. So now the unexplored nodes in our tree is node 9, node 10, node 8, node 6. Going by that first, we're going to go for node 9 or node 10. Let's go arbitrarily for node 9. The linear program that we solve in node 9 includes all the constraints in the original linear program, plus x1 is greater than or equal to 2, x2 is less than or equal to 3, x1 is less than or equal to 2, x2 is less than or equal to 0. Okay. The linear program that we solve in node 9 includes all the constraints in the node 0, plus x1 is less than or greater than or equal to 2, x1 is greater than or equal to 2, x3 is less than or equal to 3, x1 is less than or equal to 2, and x2 is less than or equal to 0. So this is the linear program that we solve in node 9. Let's solve that linear program. Let's read the linear program, solve it. The optimal objective value for the linear program in node 9 is 22.6. And let's get the optimal solution. And the optimal solution to the linear program in node 9 is x1 is 2, x3 is equal to 3, x4 is equal to 0.2. Okay, let's record that. So for the linear program that we solve in node 9, the optimal objective value is 22.6. And the optimal solution is x1 is equal to 2, x2 is equal to 0, x3 is equal to 3, and x4 is equal to 0.2. Good. So we solved the problem in we solved the linear program in node 9. This is the optimal objective value for linear program in node 9, 22.6. And this is the optimal solution to linear program in node 9, 2, 0, 3, and 0.2. Great. So then, is the optimal solution to the linear program in node 9 satisfying all of the integrality requirements? x1, x2, and x3 are all integer decision variable, are all integer valued. So then the optimal solution to the linear program in node 9 satisfies all of the integrality requirements. So by digging deeper and deeper and deeper into this node 9, we cannot get any other solutions that gives us a better objective value of 22.6. So there is no reason to dig deeper and deeper into node 9, because in node 9, we already have an integer solution that gives us an objective value of 22.6. So we stop the search in node 9. That's our first reason for stopping the search at a particular node. If the optimal solution to the linear program at the current node is feasible to the integer program, satisfying all integrality constraints, then we stop the search at the current node. So the optimal solution linear program in node 9 satisfies all of the integrality requirements, so we're going to stop the search in node 9. Furthermore, is this integer solution giving us a better objective value than the best integer solution that we found so far? Yes. The best integer solution that we found so far was giving us an objective value of 22.2. Now we found an integer solution that gives us an objective value of 22.6. Let's update the best integer solution that we found so far. So now the best integer objective value that we obtain in our tree is now best integer objective value that we obtained in our tree so far is going to be updated to 22.6. And the best integer solution that we found so far in our tree is going to be updated to 203 and 0.2. Good. Right. Looking at our tree, now we have nodes 10, 8, and 6 unexplored. Going there first, we're going to go for node 10. The linear program in node 10 includes all of the original constraints, and x1 is greater than or equal to 2, x3 is less than or equal to 3, x1 is less than or equal to 2, and x2 is greater than or equal to 1. Here is the linear program that we solve in node 10. The original constraints, x1 is greater than or equal to 2, x3 is less than or equal to 3, x1 is less than or equal to 2, and x2 is greater than or equal to 1. So this linear program that we solved in node 10, it includes everything, and x1 is greater than or equal to 2, x3 is less than or equal to 3, x1 is less than or equal to 2, and x2 is greater than or equal to 1. Let's save this. Let's bring up our Groby. Read the linear program, solve the linear program, and let's look at the optimal solution. Oh, let's read the linear, let's do it again, sorry. Let's read the linear program, solve the linear program, and let's get the optimal solution. So for the linear program that we solve in node 10, the optimal objective value is 22.2, and the values of decision variables x1, x2, and x3 are 2, 1, 2, and x4 is equal to 0. Let's record that. Here is the linear program that we solve in node 10. The optimal objective value is 22 even, and the optimal solution is 2, 1, 2, and 0. Can we stop the search? Can we stop the search? So the optimal objective value of linear program in node 10 is 22, and the optimal solution is 2, 1, 2, 0. Can we stop the search in node 10? Yes, we can stop the search in node 10 for actually two reasons. One is, in the linear program in node 10, the optimal objective value of the linear program in node 10, I'm sorry, we can stop the search in node 10 for two reasons. The optimal solution to the linear program in node 10, the optimal solution to the linear program in node 10, 2, 1, 2, 0, satisfies all of the integrality constraints. So which means that if I dig deeper and deeper and deeper into node 10, I'm not going to find a better integer solution. I'm not going to get a better objective value. So one reason that we can stop the search in node 10 is the optimal solution to linear program in node 10 satisfies all the integrality requirements. That is the first reason. And the second reason that we can stop the search in node 10 is that the optimal objective value to linear program in node 10 is 22, but the objective value of the best integer solution that we found is 22.6. So the optimal objective value to linear program in node 10 is 22. It's worse than the objective value of the best integer program that we found so far. So if we dig deeper and deeper into node 10, we're not going to find anything better than the objective value of 22.6. So we can stop the search in node 10 for that reason as well. So we're going to stop the search in node 10. So we can stop searching node 10 for the second reason as well. The optimal objective value of the linear program at the current node is worse than the optimal objective value of the best integer solution that we found so far. There are two reasons to stop the search in node 10. We stop. What is left unexplored? Node 8. The linear program in node 8 the linear program in node 8 includes all the constraints in the original linear program, plus the constraint x1 is greater than or equal to 2, plus the constraint x3 is less than or equal to 3, plus the constraint x1 is greater than or equal to 3. x1 is greater than or equal to 3. Let's write down the linear program in node. Let's write down the linear program in node 8. The linear program in node 8 includes all of the constraints in the original linear program, plus the constraint that x1 is greater than or equal to 2, plus the constraint that x3 is less than or equal to 3, plus the constraint x1 is greater than or equal to 3, and no other constraints. Great. So this is the linear program that we solve in node 10. This is the linear program that we solve in node 10. x1 is greater than or equal to 2, x3 is less than or equal to 3, and x1 is greater than or equal to 3. Good. So let's solve this linear program. Save. Read the LP, solve the LP. When we solve linear program, simply like Groby said, the linear program is infeasible or unbounded. So when we solve the linear program in node 8, Groby said the linear program in node 8 is infeasible or unbounded. Is there any chance for the linear program in node 8 to be unbounded? No. The linear program in node 5 was not unbounded. Linear program in node 8 includes more constraints than linear program in node 5. So if the linear program in node 5 is not unbounded, then the linear program in node 8 cannot be unbounded either. So the linear program in node 8 is infeasible. The linear program in node 8 is infeasible. If we dig deeper and deeper into node 8, we're going to be adding more and more and more constraints on top of the linear program in node 8. So the problem is going to get more and more and more infeasible if there is such a thing. So then there is no reason to dig further into node 8, because the linear program in node 8 is already infeasible. If you put more constraints on the linear program in node 8, it is going to keep on being more and more infeasible. Again, there is no such thing as more infeasible, but that's just so to speak. So then there is no reason to dig deeper and deeper into node 8 either. So now we have a third reason to stop the search at the current node. A third reason for stopping the search at the current node is if the linear program at the current node is infeasible, then stop the search at the current node. If the linear program at the current node is infeasible, then stop the search. At the current. That's a third reason for stopping the search at the current. Let's go back to our tree. What is the node that is left unexplored? Node 6 is left unexplored. The linear program in node 6 includes the original constraints plus the constraint that x1 is greater than or equals to, and plus the constraint that x3 is greater than or equal to 4. So the linear program in node 6, includes the original constraints plus the constraint that x1 is greater than or equal to 2, plus the constraint that x3 is greater than or equal to 4. X1 is greater than or equal to 2, plus x3 is greater than or equal to 3. Good. So that is the linear program in node 6. Let's solve the linear program in node 6. Read the linear program, solve the linear program. Again, Groby comes back and says the linear program in node 6 is infeasible or unbounded. Because the linear program in node 2 is not unbounded, the linear program in node 6 includes more constraints than the linear program in node 2. So linear program in node 6 cannot be unbounded either. So linear program in node 6 is infeasible. Which means that if we dig deeper and deeper into node 6, we're going to be adding more and more constraints into the linear program in node 6. The linear program in node 6 is still going to, if we dig deeper and deeper into node 6, we're going to add more and more constraints into the linear program in node 6. The problem is going to be, so to speak, even more and more infeasible. So we can stop the search in node 6 as well. Is there any node left unexplored in our tree? No. So we can stop the search. We've finished all of our nodes. So the best integer solution that we found is 2, 0, 3, and 0.2 for x1, x2, x3. And the optimal objective value is 22.6. This is the optimal solution to the linear program that we want to solve. So let's record it over here on the top left, if you like. Optimal solution to the IP is x1, x2, x3, x4 stars, 2, 0, 3, 0.2. And the optimal objective value is 22.6. So there is no other node left unexplored. So we found the best integer solution that we found so far is the optimal solution to the integer program. So we're done. Okay. So then let's again repeat the 3 reasons that we may want to search. Let's repeat the 3 reasons that we stop the search at a particular tree. Let's repeat the 3 reasons that we stop the search at a particular node in R3. Let's repeat the 3 reasons that we stop the search at a particular node in R3. Reason number 1. Reason number 1. If the optimal solution to the linear program if the optimal solution linear program at the current node satisfies all integrality constraints. If the optimal solution to linear program at the current node satisfies all integrality constraints, then there is no reason to dig deeper and deeper into this node. Why is that? For example, the optimal solution linear program at this node satisfies all integrality constraints, and it gives me an objective value of 22.2. If I dig deeper and deeper and deeper into this node, the objective values are going to get worse and worse and worse. I already have an integer solution that gives me an objective value of 22.2, so there is no reason to dig deeper and deeper and deeper into this node. So the first reason for stopping the search at a particular node is if the optimal solution to linear program at the current node satisfies all of the integrality requirements, there is no reason to dig deeper and deeper and deeper into that node. So that's reason number one. What is the reason number two for stopping the search at a particular node? Reason number two for stopping the search at a particular node. If the optimal objective value of the linear program, if the optimal objective value of the linear program at the current node is worse than the objective value of the best integer solution that we found so far, then we stop the search at the current node. So for example, let's say that the objective value of the best integer solution that we found so far was 22.2. Let's say the objective value of the best integer solution that we found so far was 22.2. We solved the linear program at this node. The optimal objective value of the linear program that we solved at this node was 22.16, which means that if I dig deeper and deeper and deeper into this node, the objective values are going to get worse and worse. But the objective value of the best integer solution that we found so far was 22.2. So then there is no reason to dig deeper and deeper and deeper into this node because I already have an integer solution that gives me an objective value of, I already have an integer solution that gives me an objective value of 22.2. So then the second reason that we stop the search at a particular node is if the optimal objective value of the linear program at the current node is worse than the objective value of the best integer solution that we found so far, we stop the search at the current node. And the third reason that we stop the search at the current node is if the linear program at the current node is infeasible, then we can stop the search at the current node. Good. So then when we execute the tree in this way that we did, there are two decisions that we need to make at each node of the tree. The first decision is which decision variable do we branch on? Like for example, we solved the linear program in this node. X1 did not take an integer value and X3 did not take an integer value. We decide to branch on X1. X1 is less than 1, X2 is greater than 2. We could have branched on X3. We could have branched on X3 by saying X3 is less than or equal to 3 and X3 is greater than or equal to 4. And if you branch that way, your solution, your tree would also get to the optimal solution as well. So your algorithm would have worked just as fine. So from the perspective of obtaining the optimal solution, there is no difference between branching any of the non-integer decision variables. So it's fine if you had branched on X3 over here in the first node. Okay. And the second decision that we do is whenever there are multiple unexplored nodes, we pick the one that is deepest. Again, that is a subjective decision. You could have gone breadth first. You could have picked up the highest node. That highest node could have gotten you a solution that gives you a larger objective value. But the reason that we went there first was that we tried to get to an integer solution as fast as possible. We tried like put as many constraints as possible in our decision variable so that we would get to an integer solution as fast as possible. And there are no hard and fast rules in terms of which decision variable to pick to branch on. And there are no hard and fast rules in terms of should you go depth first or breadth first. And there's a lot of like research in terms of like guessing which decision variable to branch on and whether you should go depth first or whether you should go breadth first. The good rule is whatever variable you branch on, or whether you go depth first or whether you go breadth first, this procedure is always going to get you the optimal solution. You don't need to worry about that. Okay, you're always going to get to the optimal solution. So let's go into the wrap-up mode. Stop the share. So this algorithm that we constructed that takes place by creating all these nodes over a tree is called the branch and bound algorithm. And again, at any node of the tree, we have multiple, during the course of the branch and bound, we have two decisions to make. Which fractional decision variable do we branch on, or which node do we pick up next to explore? Picking any fractional decision variable to branch on is going to work out fine. You're going to get to the optimal solution. And whether you go depth first or whether you go breadth first, whatever node you explore next, it's also not going to matter. You're still going to get to the optimal solution. Having said that, the decision variable that we pick to branch on, and whether we go depth first or breadth first, may have implications on how big the tree grows before we get to the optimal solution, okay? So the decision variable that we pick to branch on next, or whether we go depth first or breadth first, has implications on how big the tree gets before we stop this whole branch and bound procedure. And there's, again, a lot of research to guess which decision variable to branch on and whether to go depth first or breadth first. It's hard to find reliable heuristics, but one of the usable heuristics is that, let's say you have a decision, let's say you have an optimization problem where some of the decisions are more strategic or some of the decisions are more lower level decisions. Let me try to give an example. Let's say we're trying to solve an optimization problem where some of the decision variables correspond to which facilities we open, and some of the other decision variables some of the other decision variables are related to which customer sites we connect to which open facilities. Okay. Let's say we're solving an integer program where some of the decision variables correspond to which facilities we open, and some other decision variables correspond to which customer sites we connect to which facilities. Clearly, the facility opening decision variables are at a higher level. You first decide which facilities to open, and then you decide which customers to connect to which open facilities. So if you have some kind of a hierarchical structure between your decision variables, it's usually a good idea to branch on the decision variable that captures more strategic decisions, that captures the more high-level decisions. But even then, this is not like a reliable, well-cut rule that's always going to get to the optimal solution without making your tree grow too large. So there's, again, a lot of research to predict which decision variables to branch on or whether to go depth first, breadth first. So those are kind of subjective decisions that people are trying to come up with reliable rules for. But the good news is whichever variable we use to branch on, and whether we go depth first or breadth first in terms of which node to pick up to explore, this branch and bound procedure is always going to get to the optimal solution. It's just a matter of how large your tree is going to grow before you get to the optimal solution. Okay, so let's stop here. This is the branch and bound method for solving integer programs.